Knowledge includes Hichio Kim, work with Gary Shu, my student Jake McNamara, another student Huri Tarazi, with also with Sheldon Katz, and for work to appear with Miguel Montero. So these are different works, but they're actually connected in ways that I will try to explain that. So, so the basic plan of the talk is to basically review what we know about quantum field theory. Well, we know quantum field theory quite well now. It's rather well understood what constitutes a good, consistent quantum field theory. But unfortunately, the same thing we cannot say about quantum gravity. In fact, the first attempt to quantize quantum gravity, as is well known, failed when Feynman tried it in the 60s. And we later learned that string theory cures the problem. However, this is not quite an accurate description of what string theory accomplished. Feynman's problem with quantizing gravity still holds. In fact, quantum field theories that can be consistently coupled to gravity seem to be measure zero. And therefore, maybe the easier question first to approach it is to see which quantum field theories cannot be coupled to gravity consistently, because almost none of them do. So the Swampland program is to find what conditions there are to rule out quantum field theories as arising in low energy limit of quantum gravity theories. By finding these rules, we hope the aim is to actually get an understanding of what finally quantum gravity is. So this is the springboard to understanding more deeply what is quantum gravity all about. So how do we find the Swampland criteria? Well, what we have at our disposal is string constructions. So we can look at string constructions, look at what kind of consistent theories we seem to be getting, because we believe string theory is consistent, and see what quantum field theories are missing, and try to understand whether the lack of quantum field theories that we don't see in string constructions can be explained by basic principles. Basic principles, I mean, not just like saying, okay, it doesn't appear in strings, so they are not good, but something more fundamental like, okay, it's more general laws of physics like unitarity or consistency with black hole physics, anomalies, this and that. So understanding more general features of why they don't appear and try to explain them. This is of course important because to try to come up with principles based on string theory without vetting that question whether it's related to a deeper principle might lead to the string Lamppost effect, which is we get our rules based on string construction, which could mislead us. So it is crucial, it's vital to try to step back from string theory to try to get what are the basic constructions mean in terms of something which is more basic than string theory, perhaps. With doing that, when we extract these principles, it is possible that we end up with with possibilities that cannot be constructed within string theory, but it's consistent with some other constructions which we yet don't know. However, actually, one of the things I want to give evidence for today is the String Lamppost Principle, which seems to say that all consistent quantum gravity theories are part of the string landscape. And I want to use these basic facts that we are learning from string constructions and connecting it to deeper aspects of physics to see that indeed this landscape of things we get from string theory is more or less complete. So the plan of my talk is, first of all, I want to review some Swampland conditions to basically get oriented to what and apply it to the examples that I want to describe. And I basically focus on higher supersymmetric theories in this talk. So I apply these Swampland principles to supersymmetric theories with 32 supercharges. This is, for example, n=8 supersymmetric theory in 4D. Applications to supersymmetric theories with 16 supercharges, as is the case, for example, with 4D n=4, with 8 supercharges, which is n=2 in 4D, and then I'll present briefly my conclusions. So some of these Swampland criteria go a long way back. One of the basic ones, in fact, one of the most clear principled one is what's called the completeness of spectra, that if you have a gauge field, let's say P+1 form gauge field in quantum gravity, every charge p brane state appears in the spectrum, in the string spectrum, in the quantum gravity spectrum. Now, this principle is deeply related to the lack of global symmetries in consistent theories of gravity, but that's only true in d bigger than 2. because we do have quantum gravities which have only global symmetries in dimensions 2, and that shows a difference between them. Part of the motivation for this lack of global symmetries comes from consistency with black hole physics, and story changes in lower dimensions, for example, in 2D, and that explains that we can have global symmetries in 2D quantum gravity theories. So some of these swampland criteria will have exceptions when you get down to low dimensions, like 2. So in this talk, I assume a stronger version of this completeness spectra. That is, if you have a supergravity theory with supersymmetry in particular, for all charge states which are allowed by the BPS conditions, by the supersymmetric BPS conditions, there is a BPS state in the spectrum. Consequence, the completeness of spectrum is a consequence of a more general swampland conjecture, which is called the cobordism conjecture. Basically, it suggests that all the cobordism classes in a consistent theory of quantum gravity vanish. If it didn't vanish, for example, if you didn't have a complete spectrum, you could find elements in cobordism which are non-trivial, and that will, in particular, get rid of this possibility. The triviality of cobordism class is far stronger than just the completeness of spectrum, and there are other consequences. For example, if you have a theory which have a discrete gauge symmetry, that discrete gauge symmetry can be used accompanied by additional actions on space-time to create orbifolds which should be consistent backgrounds of quantum gravity. In other words, singularities like orbifolds that we are familiar with string theory, if they were not allowed, then the cobordism class would not have been trivial. So the cobordism class triviality in particular means orbifolds should be allowed. I also make a side remark about another swampland condition, which is related to the baby universe hypothesis. This is not, this swampland principle is not specifically related to what I'm going to discuss later in the talk, but since there's an interest in the subject during this during the talk, for example, the talk we heard from Henry yesterday, I think I discuss it here. So the baby universe hypothesis postulates that baby universe Hilbert space is one-dimensional in dimensions bigger than 3. Again, the restrictions to low dimensions come from the exceptions that happens in swampland criteria. And motivation for this conjecture is that we have a unique quantum gravity theory. In particular, if the baby universe was not one-dimensional, you have, as we well know from the work of Coleman and Giddens and Strominger, we know that you can have alpha parameters in the theory, which are not expectation value of dynamical fields, and that cannot happen if you have a unique theory of quantum gravity. So if you assume this hypothesis, it implies that the ensemble interpretation of holography cannot be valid in dimensions bigger than 3. So moreover, for dimensions less than or equal to 3, the ensemble interpretation of holography could be viewed as incomplete. It is a manifestation of computing observables in a standard non-ensemble higher dimensional holographic theory. So these ensemble things that we see in, for example, JT gravity would be such an example. Just to be a bit more clear, so if you take JT gravity, we know that this realizes, thanks to the beautiful work of Sad, Schenker, and Stanford, it realizes an ensemble interpretation of holography, and can be, but it turns out that, and this was nicely reviewed in talk by Henry yesterday, it can be viewed as I mentioned, by computing standard Wilson loop observables in a higher dimensional theory. In other words, when you take a trace of e to the minus HTs for a collection of Hamiltonians, seemingly disconnected, which are connected through an ensemble average, which in this case I'm denoting by J, this is very much similar to what we do, for example, in path integral and gauge theories. We take dA, e to the minus the action for the gauge connections, and the Wilson loop observables. In this context, the choice of the ensemble is related to the choice of the background. The choice of the observables that you're inserting is the Wilson loop observables, so the Hamiltonians would be related to the Wilson loop observables in the gauge theory. If you take a gauge theory which has a large N description, then of course you get 2 Fremont surfaces, and that would be the worksheet theory of this large N description of this theory. And it turns out that the JT gravity exactly fits with this picture. And it turns out that the words you get end up in this way as the worksheet theory of the 60 topological string theory on a Calabi threefold given by y squared plus sine squared root x plus u squared plus v squared, which is equivalent to Mirzakhani's model in terms of its amplitudes. So matrix model, and moreover, the matrix model ensemble description of JT gravity is a manifestation of standard holography in this 60 theory. We do not need an ensemble interpretation of the 60 topological theory, which is called the Caudaret-Spencer theory of gravity, to try to describe this, map between the matrix model and the JT gravity. And this, I would like to say, this is more general than this example, because in fact, it's true for any large N description. You can just repeat this statement for any large N theory. The worksheet theory of the perturbative worksheet theory in the large N expansion is nothing but this description of a 2D, and the JT gravity is just an example of that. And there could be potentially a 3D version of this, though that's not clear, where the worksheet will be replaced by the M2 branes. But beyond 3 dimensions, it should not be possible because of the Hilbert space of the baby universe being one-dimensional. This is an example of the string lamppost principle, by the way, basically an example, namely JT gravity, which seemed to be far from discussions of string theory, can be embedded in string theory. JT gravity, in fact, arises from type 2B string theory on this non-local Calabi. And moreover, you take I talked about topological string. You might say, what does this have to do with the regular string? Well, you can phrase it in terms of the regular superstring. It corresponds to Calabi threefold compactification times R4 twisted by omega background of Nekrasov. So we can just describe it in this way as well. So to say that the JT gravity is a theory of 2D gravity and not part of an ensemble of a higher dimensional theory like in Caudaret-Spencer theory is akin to saying the type 2B superstring is the theory of 2D superconformal gravity, basically the worksheet of string. Of course, we know that for every vertex operator, we get some description, but the totality of all these vertex operators together and the totality of these ensembles tell you that there's a higher dimensional, better perspective, which is this 10D perspective, and the same is true with JT gravity. So I move on to other criteria, unitarity. Unitarity, every quantum gravity should be unitary. This is one of the basic assumptions related to no loss of information. A famous application of it is in the context of black hole physics and its unitary evolution. It should apply to the effective theory on all stable branes, and in particular to BPS branes in the theory. For example, if we have a one brane in the theory with central charge C left, C right, we must have the central charges be positive. Similarly, if we have a gauge group, a gauge symmetry group G in the full theory, it should lead to a conserved global current on the brane. And assuming we have left moving, suppose it's left moving, J left current with level K left, which is related to the anomaly of this, we must have the K left being positive. And from the WZW model, we know that the central charge is related to the level times the dimension of the group divided by the level plus the dual Coxeter number. Now, the unitarity of the theory implies that the central charge of this gauge group piece, of the global symmetry piece, G, should be less than the central charge of the theory, because the balance of them should be positive to be filled by some other degrees of freedom on the string. So this is an example of the unitarity. The theory should have no anomalies. Of course, the quantum gravity should have no gravitational mix or other anomalies. And this is perhaps too obvious to even state. Of course, quantum field theory should be anomaly free. And if you add gravity to the mix, you must also make sure gravity is anomaly free. So this turns out also to be very useful for many applications, and I'll give you some examples later. In the presence of defects, the bulk gravitational theories may appear anomalous, but their anomaly is canceled due to the opposite anomaly on the defect through the anomaly inflow. And this is a well-known the inflow mechanism. For example, if you consider a one brane with field strength H, satisfying DH is proportional to the Pontryagin class and the instanton density, the coefficient in front of them give you the central charges, which corresponds to the gravitational and global anomalies, if you gauge them. And this given by C left minus C right is A, and B is K left minus K right. We also need a strong version of the distance conjecture. The Swampland Distance Conjecture says that in a quantum theory of gravity, a large excursion in the expectation value of massless scalar field leads to an exponentially light tower of states. Now, what is the motivation for this conjecture? Well, in a sense, the distance conjecture is a rephrasing of the expectation that at large distances in field space, in massless field space, we end up with dual description. In other words, the tower of states that we get is what constitutes the dual description of the theory in this case. Now, this principle, we don't have a really good proof of this principle. We don't have something like black hole physics or something which tells you it had to happen. So it would be great to have a deeper understanding of this, but we have by now overwhelming evidence for amazing things this leads to, and we have seen it in all parts of string theory for sure. And so I will take this as a principle, and it still needs to have a deeper understanding, but I will take this as a principle of Swampland. There's a stronger version of this conjecture, which is what was the motivation for the original conjecture, is that at large distance and field space, the tower of states, the tower of light states that we get, the exponentially light tower of states, we get constitutes a degree of freedom of a dual description. And we will assume the stronger version of this conjecture for my talk. And as we will see that for the cases with higher supersymmetries, like the case with 16 supercharges, this will have important implications for us. Okay, so now I start by trying to apply these principles, these examples to the various examples in the context of supersymmetric theories. What I want to say about these, just to give you an overview of what I just covered, I talked about a number of these swampland conditions, and by now there has been a huge collection of these swampland criteria, and it's growing, but all of them in some sense are connected together. So there's interconnectivity of these ideas, and the fact that one reinforces the other gives us more confidence about their validity. And here I only have talked about only a few of them, and there are many more, and there has been some beautiful work by many people in the past few years which shows all this. So I only covered the part that I need for my talk. So so now I come to applying it to supersymmetric theories. Let's start with theories with 32 supercharges. This is a theory with maximum amount of supersymmetry, and I will study this consequence of this in my talk and in all these supersymmetric theories for Minkowski backgrounds. Now, for 32 supercharges, the low energy limit is completely fixed by supersymmetry. D equals to 11 is realized by M theory. E equals to 10 is realized by two types, the 2, 0 supersymmetric one, which is realized by type 2B strings, and 1, 1 supersymmetric theory is realized by type 2A, or equivalently M theory on a circle. And dimensions less than 10 are given by toroidal compactifications of the above. Now, this might sound like a boring example because everything is fixed by supersymmetry, but actually is the first evidence for the String Lamppost principle. It appears to be okay, and indeed is realized in string theory. It may have not been realized in string theory, so it did not have to be that we have it as part of the string landscape. So even though it sounds like it's a boring example, it is actually an example of the String Lamppost principle. To get to more sophisticated cases, let's go down in the amount of supersymmetry. Of course, as we go down in the amount of supersymmetry, the life gets more complicated. The maximum amount of, the next maximum one we want to discuss is the n equal to 16, which will be happening, for example, beginning in 10 dimensions. So in 10 dimensions, this chiral theory, which has d equals to 10, and n equals to 16, which is denoted as 1, 0 supersymmetry. And the theory is anomalous unless there is very special groups, as Green and Short discovered long ago. So these four groups, E8 cross E8, SO32, E8 times U1 to 248, and U1 to 496, cancel anomalies very non-trivially. Well, the first two certainly non-trivially, and the latter two a bit more trivially. Now, could it be, and only the first two have been, of course, constructed in the string landscape. Could it be that the last two are just shows that the String Lamppost principle is incorrect, that there could be other theories we haven't discovered, which has nothing to do with string theory, which realizes these two theories? It turns out that the simple swampland criteria we discussed ruled out the latter two theories, consistent with the fact that they do not appear in the string landscape. So let me try to review how that comes about. So this theory has a two-form gauge field B, antisymmetric B field. And according to the completeness conjecture, we must have a BPS string with 0, 8 supersymmetry. You can use the anomaly inflow, which is, in this case, its coefficient is fixed by the consideration of the anomaly cancellations. And one finds, ignoring the center of mass contribution, that C left is 16, C right is 0, and K left is 1. There's a current algebra associated to the group and should be left moving with central charge 1 and the level 1, and the central charge of the total thing on the left is 16. So we must have a current algebra on the left because C right is 0 and CG is equal to less than or equal to 16 because the C left is 16. So whatever we put in for the central charge of the current algebra better be less than 16. It turns out that E8 cross E8 and SO32 at level 1, both of them saturate this bound. It's exactly 16. So there's no other degree of freedom as far as the infrared degrees of freedom on the brane is concerned. But E8 times U1 to the 248 or U1 to 496, if you take level 1, you get the central charge bigger than the 16 that's allowed. And these two theories, if they existed, would have violated unitarity. So they don't exist. And that's consistent. So we rule them out by unitarity of quantum theory. So we are fine with 10 dimensions. Now you saw anomaly play the crucial role. Then you might wonder, what about d less than 10, where anomaly is not going to be there, for at least for chiral reasons? There's only one such case, which is for dimensions bigger than 4, which is chiral, which is d equal to 6, n equal to 2, 0 supersymmetric theory. And the matter content in this case is fixed by anomaly, and indeed it's realized by type 2b on K3. This is again a good illustration of the String Lamppost principle. Now the theory is non-chiral for all the rest, and how do we rule it out? That's for dimensions bigger than or equal to 4 that I'm talking about. How do we rule out theories? Or maybe we cannot rule out theories. Maybe all ranks are allowed as naively expected. The simplest toroidal compactifications of heterotic string or type 1 strings, you get the rank is equal to 26 minus d. So for example, in d equals to 9, you get rank 17 if you compactify the theory on a circle. But there are more sophisticated constructions known. For example, in dimension 9, there are 3 possible ranks seems to appear: rank 1, rank 9, and rank 17. Rank 1 can be constructed using M theory on Klein bottle. Rank 9 can be constructed using heterotic string, heterotic CHL string on E8, which gives rise to E8 cross U1. And rank 17, I already said, is compactification of heterotic on a circle. For example, E8 cross E8 times U1. And these are the only ranks we get. Of course, we can deform with Wilson lines, but it doesn't change the rank. Now, global anomalies, in this case, actually exists. There's a global gravitational anomalies, which gives you that the rank of the gauge group should be odd. So this is consistent with the fact that we find the ranks 1, 9, and 17. But it doesn't quite explain why there are no, for example, 3, 5, 7, etc. And it doesn't explain why don't we have higher odd numbers we get bigger than 17. So it tells you something, but it's not enough to get exactly this set. There are, if you continue down the different dimensions and use these more sophisticated compactification beyond just the toroidal ones, you get ranks which go like this: 1, 9, 17, dimension 9. In dimension 8, you get 2, 10, and 18. In dimension 7, you get 3, 5, 7, 11, 19, and so on. So you see that there are some gaps. There are gaps mod 8 here in the first 2 cases, dimension 9 and 8. So you have 1 mod 8 in dimension 9 and 2 mod 8 in dimension 8. But in dimension 7, you get 1 mod 2. And in fact, you still have some gaps, further gaps like here. But then, yeah, there's this more structure here that needs to be explained. And we don't get anything higher than 26 minus d, 17, 18, 19, and so on are the highest one as we go down the dimension. Now, it turns out that, of course, all these theories admit BPS strings. And however, unlike the 10-dimensional case, the supergravity anomalies is not powerful enough to fix the coefficient for these anomaly inflows. And in fact, there are two possible infrared supersymmetries that can be realized on string theory. It could be either 8-0, there could be different amount of supersymmetry with their 8 supersymmetry or 8-8 supersymmetry. Left and right movers are only on one side. So if you have only on one side, you can show that the central charge on the left moving part of the string is 24 times kappa plus 2 minus d, and C right is 12 times kappa minus 1, where you cannot determine kappa based on gravity theory alone, because supergravity does not fix the coefficient of the H term, so you have an unknown parameter kappa in this description. However, if you use the strong version of distance conjecture, which tells you that if you take the string and compactify the string theory on one more circle, then you can go to the limit where the string circle circumference goes to 0 size. And due to the high amount of supersymmetry, you can have non-randomization of the moduli space. Using this and assuming that we have a dual description, which is the strong version of distance conjecture tells you, automatically implies that the winding strings must constitute the dual graviton description of the momentum modes. And the winding strings having spin no more than 2, in other words, the dual graviton cannot have spin more than 2, that fact, the fact that the winding string cannot have, in the ground state of the winding string on a circle, you cannot have a spin bigger than 2, relates to the R symmetry on the supersymmetric theory, and that restricts kappa. And that restricts to kappa less than or equal to 1. And since you have this formula for C right, ignoring the central mass and so forth, you learn that kappa cannot be anything but 1. And if kappa is 1, you find that the central charge is 26 minus d. And indeed, this also implies that the rank of the groups that you get are always less than or equal to 26 minus d by the formula for the central charge for the WZW models. So this gives you a restriction that we had for the 0,8 theories. For the 8,8 theories, which could happen, and in fact it does happen, that you can get an enhanced supersymmetry in the infrared on the brain. So you get an enhanced supersymmetry in the IR, which sometimes happens in conformal field theories. In the Klein-Bottle compactification on M theory is one example of it. And doing the same exercises above gives you that the C left, C right is 10 minus d comma 0. And in this case, you learn that the rank of the group is less than 10 minus d, which in turn is less than 26 minus d. So this upper bound on the rank, which is 26 minus d, is indeed seems to be explained in this construction. This result in particular implies that in d equals to 4, for n equals to 4 supersymmetry, theories with rank bigger than 22 are in the swampland. In particular, n equals to 4 supersymmetric Yang Mills SUN for n bigger than 23 is in the swampland. In fact, SU23 is in the heterotic landscape, so it's a sharp bound. So SU23 is allowed, but SU24 is not allowed. This is a striking example. Even a beautiful, finite quantum field theory, like what can be more simple and more elegant theory than n equals to 4 and 4D, even such a beautiful theory cannot be consistent generally when you couple to gravity. And only a finite number of them are consistent, namely all the ones, well, not all the ones, but at least they should satisfy the rank should be less than less than or equal to 22. So, of course, this does not mean you cannot get n equals to 4 SUN Yang Mills in string theory. In fact, we know we can get it. So for example, they are realized on ND3 branes in 10D. However, gravity is dynamical in 10 dimensions, not in 4 dimensions. Here I'm talking about restrictions where you have 0 modes of the gravity in 4D, not in 10D. And therefore, we see that there's dramatically different situation. So again, this is part of the story. You can get all these consistent quantum field theories, and probably it's true that you can get all quantum field theories which are consistent in string theory in some way or another, but it doesn't mean it couples to gravity in the dimensions that they are living in. They could be realized as defects. But there's more structure in what we can get in string landscapes than the rank. We can apply the swampland ideas, and in fact, to explain why do we get in dimension 9 rank being 1, 9, and 17, and nothing else. So we have explained why the rank is less than or equal to 17. We know by the global gravitational anomalies they are odd, but why should it be only 1 and 9 and 17? Well, the theory in 9 dimension has a PC symmetry, and according to the cobordism conjecture, we should allow for the orbifolds of the type T3 mod Z2. So the singularities of orbitals should be allowed, otherwise the cobordism classes will be non-trivial. So if we take orbifolds of T3 mod Z2 accompanied by the PC symmetry, this theory leads to a theory in 6D which satisfies n equals to 1, 0 supersymmetry. So you reduce the supersymmetry by half, and it's a chiral theory. So this existence of this orbifold allows for you to get from a non-chiral theory a chiral theory. This is similar to what happens in M theory in Hojawa-Witten construction, which is not chiral. By doing orbifolds on a circle with Z2 with allowing singularities, you get a chiral theory in lower dimensions. Same thing happens in general in this case. And now if you count how many, so then you can study the spectrum of the theory. This theory is flat everywhere except near these singularities, and you have to assess what happens at singularities. Using Dirac quantization arguments by Tachikova and Yonekura, you can show that the contributions for the number of multiplets coming from each one of these fixed points is integer, and therefore using the anomalies, using the fact that you have 8 fixed points gives you the, even though we do not know how many each fixed point may contribute to the tensor or vector or hypers, it will give you a mod 8 condition. So if you then go down to 6D and consider the 6D anomalies, you get a formula for cancellation of the global, cancellation of gravitational anomalies, and you find based on this that the rank of the group must be 1 mod 8. And this is consistent with what we expected, 1, 9, and 17. It's crucial that this dimension is, by the way, a 5 plane that has this singularity, and a 5 brane has this singularity. In the lower one, you could have gotten fractional ones, as for example is known in M theory constructions with lower dimensions, would get fractional contributions. But in this dimension, you cannot, as was argued in this paper. Now, similar arguments for 8 and 7 dimensions also work. So if you compactify the 8-dimensional theory on T3 mod Z2, so you get the theory in 5 dimensions, or if you take the 7-dimensional theory and compactify it on a circle mod Z2, absence of global anomalies in 5D case for the first one, and absence of chiral anomalies for the second case in the 6D lead to the condition that in 8 dimensions, the rank is 2 mod 8, and in dimension 7, the rank is 1 mod 2, exactly as we see in the structures that appear in the string landscape. So now let's go down in the number of supersymmetries. How about theories with 8 supercharges? Well, the first case we encounter in this context is D equal to 6 with 1, 0 supersymmetry. The theory is chiral, and anomaly cancellation puts severe restrictions, as has been studied comprehensively. On the other hand, these theories admit many different kinds of strings, many different ones, depending on how many tensor multiplets you have. And you can get restrictions, again, using the same trick we used for the anomaly inflow. And I will just give you one example. More examples can be found in the papers I cited already. So if you say that, if you look at one of the anomaly cancellation conditions, you get if you have 8K plus 9 tensors, and if you have a gauge group G is equal to E8 to the K, for arbitrary K, the anomalies cancel. However, if you look at the strings in this context, you must have the condition that for every string that in the theory, the central charge of the string of the gauge groups, in this case E8, which satisfies 248 times the level of them, divided by K pi plus 30, which is the dual constant number of E8, this sum should be less than or equal to the central charge that the string realizes. And in this case, you can compute these anomaly, using anomaly inflows, what these coefficients can be. And this condition leads to the statement that K cannot be bigger than 2. So it rules out K bigger than 2, and only K equals to 1 and 2 could be allowed. And indeed, K equals to 1 and 2 are realized in string theory using the F theory construction. And there are similar other kind of examples studied here as well. So the main point here is that the simple ideas like unitarity and anomaly inflow and so forth can put severe restrictions, which reinforces the idea that of the string Lamppost principle. String theory is giving us all the things that could be possibly consistent. We are not missing anything. So going further down in dimensions, we can go to, again, with 8 supercharges, we can go to n equals to 1 supersymmetric theories in 5 dimensions.
This is a 5-minute warning.
Okay, thank you. So, so we can again study the same kind of restrictions. In these theories, again, we have strings, BPS strings, and we can look at unitarity bounds and the anomaly inflow restrictions for these theories. So as an example, we can just a number of examples in our paper, but let me just give you just one sample of it. You can consider a theory in 5D, which is who has no vector multiplets, but has hypermultiplets, and graviphoton, of course, as part of the supergravity multiplet. Suppose the supergravity multiplet to the graviphoton has Chern-Simon terms, A wedge F with coefficient K, and A wedge R with coefficient K prime. So as you move in the hypermultiplet moduli, you can get enhanced gauge symmetries. Even though you don't start with any vector multiplets, you could end up with vector multiplets by tuning. In other words, you can think about hypermultiplets as the quote unquote the Higgs branch of a would-be gauge symmetry that has disappeared. And this does happen, of course, in string theory. It's possible to show, using again the unitarity on the strings, that for non-abelian gauge groups G, the rank of the gauge group should be less than or equal to some of these two coefficients, K plus K prime minus 3. This looks like a very strange statement from just looking from the viewpoint of the low energy supergravity. Why is it that the rank of the gauge group appearing in the theory should be bounded by these coefficients, but it follows simply from the unitarity conditions I just said? And indeed, if you look at the string landscape, an example of this situation is realized by the famous M-theory compactification on quintic. If you take the quintic case, you find that K plus K prime minus 3 in that case becomes 52. So you find the rank of the groups that you can get is less than or equal to 52. And in this case, it's consistent with the geometrical bound that in this quintic case, the rank should be less than or equal to 44. So it shows the power of this unitarity argument here. So since I'm beginning to finish, I run out of time, let me finish my talk. So we have found further evidence for string Lamppost principle, Swampland criteria, which are potentially valid beyond string theory and could have led to new theories, could have led to new possibilities, at least in theories with higher supersymmetry, seem to reproduce the string landscape. Of course, we haven't reproduced every aspect of string landscape, even in the higher dimensional theories, higher supersymmetric theories. For example, we didn't explain or we didn't obtain all the possible gauge groups that you can get. So there are much more refined questions that we can get. For example, in dimension 9, the G2 gauge group does not seem to appear as a possibility in the string landscape. What's the reason for this? And there's no explanation for that. So we're currently trying to find what are these ideas that explain that. Is there another idea we are missing in the swampland, or indeed that's some other construction that should do it? So these are the kind of questions that are natural to ask in this context. So, and also, for example, in dimension 7, we saw that the rank, not all the odd ranks less than the maximum allowed was appearing. There were some gaps. Can we expand those extra gaps further? And we can explore the theories with n equal to 8 supercharges a bit more deeply. The first goal is to show, just like we do it for the cases with 16 and 32 supercharges, that there are only a finite number of them. Even by now, we have a huge number of these consistent looking theories like cancel anomalies in 6D with n equals to 1 supersymmetry, but we cannot construct them in string theory. So the question is string Lamppost principle correct? Are there an infinite class of them that cannot be obtained in string theory, or there's a reason that they are inconsistent? So we should be vigilant and try to see if it's indeed true the string Lamppost principle, trying to push the boundaries and trying to understand these cases. Of course, we should try to also go to lower supersymmetric cases. That's going to be much more challenging when you go to lower supersymmetric cases. For example, n equals to 4 supercharges, which means equivalent to 4D n equals to 1 supersymmetric theory. In this case, you typically end up getting superpotentials. So therefore, to study these theories, you will have a harder time. If you want to find critical points and so on. And indeed, it seems like n equals to 1 supersymmetric theories in 4 dimensions, unless they are secretly related to these higher supersymmetric theories, seem to generate superpotential. So those are more interesting and more challenging to study. So I think at this stage I'll stop my talk. Thank you very much.
Thank you. There were a number of questions in the chat. I see any raised hands.
I cannot hear you.
Okay, Cumrun, I have the following question. Well, your first example involved the string that was supposed to have 0, 8 supersymmetry. In a certain model, the completeness principle implied that there was a string with a certain charge.
Yes.
But it wasn't obvious that the string has to have 0, 8 supersymmetry.
Yes, that's correct.
Later in the talk, similar questions came up at multiple points.
Yes, yes. Good point, Ed. I think I mentioned, maybe I said it too quickly at one of my first transparencies. I said I would take the stronger version of the completeness hypothesis. That is, if you have got the supergravity with a BPS condition allowing a supersymmetric one, the supersymmetric BPS is in the spectrum. So I assume that for this.
Okay, if we assume that, then it's all right. But then it's a little bit less clear that one proves that various things are in the swamplands.
Well, we don't have a counterexample to that, though.
I'll think about that.
So there's a question by Nadi Cyber. Please unmute yourself, ask the question.
Yeah, it's a follow-up on the same question. It was also on the chat. What is the motivation for this assumption? The stronger version, the one that for every charge there exists a BPS state.
Well,
is it because that's what appears in examples, or is there a general principle way?
Well, there's the principle. There's no APR. There's a principle in the same sense as in black hole. Namely, in the context of black holes, one of the motivation for completeness hypothesis is that you can have a black hole solutions. The same thing appears for black hole. So if you have a black hole BPS string solution, you should be able to get them in string theory. That's the motivation. So it's the same reasoning. So in other words, if you believe that the black hole was a good motivation for completeness hypothesis, then if there's a BPS black hole, that's also a good motivation for the other one.
Isn't this a stronger assumption? So imagine there is a black hole with energy, which is the BPS bound plus epsilon.
Well, this is when you say BPS bound from epsilon, yes, you can assume that the BPS construction seems to work for any black hole. So therefore you can assume it. There are two motivations. One is the black hole, and the other ones, there are no counterexamples. So, I mean, I think it'd be interesting to try to find counterexamples, certainly. And it'd be good to try to find counterexamples.
Thank you.
But motivation is black holes, really.
Guralashmi Subramanian, please ask your question.
Yeah, thanks for the nice talk. So I just wanted to know, so all this analysis have been carried out with Minkowski, in the Minkowski space, right?
Yes.
So if we consider de Sitter space, does that have any change in the constraints?
You mean ADS space?
No, in the, like for the de Sitter space?
Well, de Sitter space has its own host of issues that we can deal with, but those existence of de Sitter itself is in question. But you could have asked about the ADS, where we do have a huge number of examples. Which one are we talking about? If you have only about de Sitter space, then we have to describe whether or not there are stable de Sitter spaces. We don't, in string theory, we don't believe we have stable de Sitter space, and whether or not they're metastable or whatnot is still being debated.
Right. So what's there for the ADS? Like,
for the ADS case, one of the things that we learned about these from the Swampland is that when we talk about ADS holography, for example, it is always accompanied by an extra space, and that extra space is crucial to describe it by. So I'll give an example. Suppose you take ADS 7 times S4 holography for M5 branes. in that context, you might easily think that, okay, so you have an ADS7 as a holography to the other one and ignore the S4 for the discussion, think about the 7-dimensional space. And then you can say, okay, so we seem to be getting only a finite number of possibilities in these Minkowski theories, but that's not true in the ADS case. For example, you take ADS7 times S4 and you mod that by a Zn symmetry, which rotates the sphere, the S4, with fixed points on the north and the south pole, giving you an -1 singularities for any n. So therefore, you get an ADS7, an arbitrary gauge symmetry, SUN times SUN, coming from the north pole and south pole for any n. So therefore, you would say, okay, in 7 dimensions, I found that the theory can have arbitrarily large gauge group, SUN times SUN. So what is this about all these bounds, about finiteness that we're talking about in Minkowski? And so the fallacy in that way of thinking is that what's happening is that ADS7 is not by itself consistent. It's actually important that S4 has a scale of S4 is not decoupled from S7. So when we talk about ADS7 times S4, we should not view this as 7-dimensional gravity, but more 11-dimensional gravity. And when you talk about ADS7 times S4 with these fixed points, these are just gauge theories living on the defects in 11 dimensions, which we know is allowed even in 10-dimensional type 2B, for example, on ND3 branes. So when you think about the ADS in the concept of swampland, you have to take into account the full space. And people have talked about various kind of scale separation issues that come from that and so forth. So there's a whole host of conditions from swampland which describes ADS. I wish I had more time, or other speakers, maybe if they had been invited to give a talk here, they could have covered much more about ADS, which I know is of interest to a large community here.
Okay. And I just have one more short question. So for the D equal to 9, 8, and 7, we have been deriving some ranks, right? So for the D equal to 6 case, after we do the toroidal compactification, do we get any kind of constraint?
I think as you go down, I don't remember whether it starts with 6 or not. I think after a while, you don't get any gaps in the ranks, except maybe like, I don't remember when it was D equals to 4, you get all of them on, but then suddenly one gap. So it's not mod condition anymore. So it's already like in 7 dimensions, the condition was a bit funny. It was like 3, 5, etc. And then there were some funny gaps. And we don't have an explanation of those funny gaps. And so we still have to understand better whether or not these funny gaps can be explained by some principle.
All right, okay, thank you.
You're welcome.
Juan, please ask your question.
Yeah, so I would like to follow up with Subramanian's questions. If you have a universe like ours, which is not a stable de Sitter, is let's say metastable, close to the Sitter or whatever our universe is, do any of these bounds apply?
Well, presumably that's related to the question of going down in the number of supersymmetries. I think from what we have learned in the context of Minkowski with higher supersymmetric ones is that we seem to get a finite number of possible gauge groups. So there's finite number of possibilities. Whether or not this carries over to lower supersymmetric case, I would expect yes, why not? But I don't think we are at that stage yet. So I think technically we have not advanced as much to be able to answer your question definitively, but if I were to guess, I would say yes.
Thank you.
Well,
Daniel Harlow.
Yeah, I just wanted to briefly comment on this question of whether or not these conjectures are supposed to hold in low numbers of dimensions. So this is something that Hiroshi and I also worried about when we were writing our papers. I think the following statement is true. So if you have a theory of quantum gravity, which is rich enough to have a black hole information problem, then these conjectures should hold. The cases where they don't are these kind of funny, low dimensional, renormalizable theories of quantum gravity that make sense with a local Lagrangian that's renormalizable. And so, for those ones, I think they just are going to work in a very different way than theories in higher dimensions where you need to have holography. Because certainly for us, holography was the fundamental input. If you don't have that, if you can just work in the bulk, then there's no reason to believe any of these conjectures.
Yes, I think that's a good point, Daniel. I agree with you. I think these are exotic cases that happen to be exceptions in this sense. And in fact, I believe that every theory that you get from string compactification will not be an exception.
Yeah, I agree.
So in view of time, let's thank Cumrun again.
Thank you.
Please unmute yourself and clap if you want, or use the things. Thank you very much. Let's start getting ready for our next speaker, who is Ashok Sen.